Okay, welcome to the New England Dynamics and Number Theory seminar. It's another Thursday, and Lem, could you please introduce the speaker?
So welcome everyone, and we're happy to host Mikolaj from University of Chicago, Mikolaj Fraczyk. He's going to talk about the thin part of arithmetic orbifolds, and some other parts of the title that are relevant are the Margulis lemma and number theoretic adaptations of it. Mikolaj?
Yeah, thanks for the introduction. It's a pleasure to talk at the seminar. And did I forget my full title? Or okay. I thought that
it was more like a subtitle or abstract.
I see.
I took the opportunity to insert some additional things for everyone.
Yeah, thank you. So this is, of course, a correct addition because I'll be talking at some point about arithmetic adaptation of the Margulis lemma. But let me start with the basics. So I want to introduce the objects that I will be interested in. So arithmetic orbifolds, or instead I might call them locally symmetric spaces. Okay, so let me start with the general setting, and then I'll give some examples of particular families of interesting arithmetic orbifolds. So in general, we'll start with G, which is a semi-simple Lie group. I will select K a maximal compact subgroup. And X will be, in my talk, it will always be the quotient G mod K, which can be endowed with a canonical Riemannian metric, and this is the symmetric space of G. And we have that the isometry group of X, at least, orientation preserving isometry group of X is equal to G up to isogeny. So in fact, it doesn't hurt to think of G as the isometry group of X. And we also have gamma in G, which is a lattice. In my talk, this lattice will be arithmetic, but in general, it doesn't have to be. And a locally symmetric space is a quotient of the form X mod gamma. And if this is locally symmetric space. And if lattice is arithmetic, I'll call this space arithmetic as well. Okay, and an example of a family of local arithmetic spaces are arithmetic hyperbolic three manifolds or two manifolds. So let's construct some such families. So we let big K be equal to either R or C, and we can choose a number field K such that the real places of K, so K tensor R, sorry, Archimedean places of K are first is big K, and then I have some power of R, so this would be R to some power, so yeah, to something. And then once I have a number field like this, I can choose a quaternion algebra. Let's call it big A over K, such that when you tensor with R, so this quaternion algebra becomes isomorphic to, so I tensor over R with R over Q, this tensors over Q. This becomes isomorphic to 2x2 matrices over big K, so complex or real, and the remainder is just the Hamilton quaternions. So those are, and there is some power, maybe let me call it S. S can be computed from the degree of K and degree of big K over Q over R. So those are Hamilton quaternions. So there are plenty of ways to arrange for such quaternion algebra. If K has this splitting over R, we can always find such A. And then I can choose an order O in A, which is kind of like a ring of integers, but in a quaternion algebra. So full rank, I don't know, rank 4. Okay, submodule. Of A. And then finally, I can consider the group of units. So this is O1, is the group of elements in my order, which have quaternion norm 1. So, and this quaternion norm, you can think of it as determinant. It's quaternion algebra becomes the group matrix algebra over some extension, and then the norm, quaternion norm, becomes just the determinant. So this is a multiplicative subgroup of A, and now the projection of O1 onto the M to K factor is contained in SL2K. And moreover, we know that it is a lattice, it is an arithmetic lattice in SL2K. And this lattice is even co-compact if A is not split. So in most vast majority of cases, this lattice will be co-compact. So if K is equal to R, in this way, the quotients of, so let's denote this lattice gamma O1. So if K is equal to R, then the quotients of X, which is in this case hyperbolic 2 space, those quotients are Shimura curves. And if K is equal to C, then the symmetric space can be identified with 3-dimensional hyperbolic space, and those quotients are arithmetic hyperbolic 3 manifolds. So not all hyperbolic arithmetic free manifolds arise in this way, because not every arithmetic lattice is of the form gamma O1, but everyone is commensurable to it. So in some sense, in this way, we get handle on all the arithmetic hyperbolic free manifolds. So, and you can repeat those games for any group, and you get the family of arithmetic hyperbolic free manifolds. I think they're interesting just from pure number theoretical point of view, but also from the point of view of rigidity questions. So arithmetic manifolds, hyperbolic manifolds, and in general, arithmetic orbifolds behave sometimes differently than non-arithmetic ones. So we would like to understand the geometry of those families of arithmetic orbifolds, and in particular, how complex can they get in terms of the volume. So let me introduce a few measures of complexity, and we'll start with the injectivity radius. And I'll switch back to the general case of a symmetric space. So let X be a point in a locally symmetric space X. I will also write D from X to R plus for the Riemannian metric, for the metric of X. So if I have a small point, small x in gamma of X, I define the injectivity radius. Of the space at the point X, move it here, as the supremum of R, so supremum of all radii, non-negative radii, such that the ball of radius R around the point X lifts isometrically to X. So let me draw a picture. What does it mean that this ball lifts isometrically to X? Well, the lift is always, if it exists, is always a local isometry. So the only bad thing that could happen is that there are some overlaps. So let me draw this space. So the only space, locally symmetric spaces that I know how to draw are the hyperbolic surfaces. So let me draw those, one of those. Yeah, it will have some number of holes inside. So now the spectral radius, sorry, the injectivity radius will be small whenever we are in some kind of a collar, which is quite thin. So if I were to draw the thin part where the injectivity radius is small, I would draw this, possibly this, this, and this. And this leads me to the next definition. So the thin part of the manifold, which is denoted like this, X mod gamma less or equal to R. So this is what I call R thin part. This is the set of all points X in the quotient such that the injectivity radius at X is less or equal to R. Okay, so the kind of from topological point of view, the parts of the space where the topology can get complicated are exactly those where the injectivity radius is small. So one way of saying that the complexity of arithmetic orbifolds is controlled by volume is showing that this complicated thin part is very small compared to volume. So this leads me to the next definition of Benjamini-Schramm convergence. So given a, let's look at this manifold again. So I can ask the following question. So let me choose a random point of this manifold. And what are the chances that I will see that I'm on a quotient of the symmetric space in a radius within the radius R from the point of view of this point? So it turns out that typically in arithmetic orbifold, from most points, we don't really see the quotient structure. So when the orbifold is large, for most points, the injective radius will be large. So this was, I don't know who, I think Sarnak was one of the first people who conjectured that. This property is also shared by random hyperbolic surfaces and in some sense by random graphs. So I think first motivation for this conjecture was that people believed that that hyperbolic three manifolds in some sense share some similarities with random graphs. So the way to formalize it is to say that any sequence of arithmetic hyperbolic orbifolds converges Benjamin-Schramm to the universal cover, and in general this definition says the following. So we say that a sequence of arithmetic quotients of x converges Benjamin-Schramm to x if for every radius r negative we have the following. So the limit as n goes to infinity of the quotient of the volume of the r-thin part divided by the total volume of x mod gamma n goes to 0. So in other words, the r-thin part becomes negligible. So if we have such a statement for a sequence of manifolds or orbifolds, it has some pretty strong consequences for the growth of topological invariance. For example, there is the following result, theorem by Abert, Bergeron, Gelander, and okay, was the last author? I think I forgot. Let me maybe go back to this. So if X is a locally symmetric space, so X is as above, and we have a sequence of arithmetic quotients, sequence of any quotients really of X, which converges Benjamin-Schramm to X, then the limits of normalized Betti numbers, so as n goes to infinity, I take the quotient of the volume of the dimension of homology group, or homology or cohomology, this works for both, of the manifold x mod gamma n with coefficients in R divided by the volume. This limit exists and is controlled by so-called kth L2 Betti number of the symmetric space X. So this number is, as I said, this is L2 Betti number. And although definitions of L2 Betti numbers is not the simplest one, it's explicitly computable for any X. It's actually explicitly computed, not just computable. So there are tables for any X. this is due to Olbrich. And so this gives us perfect knowledge about the growth of the Betti numbers. And there are, in some cases, you can upgrade it to some other topological invariants. So I think that that's one of the maybe interesting motivations to talk about Benjamin-Schramm convergence. So we have this convergence of Betti numbers. You can also replace R by certain coefficient systems. It can be made quite general. There is also a conjecture, which is now a theorem. So let me state it first as a conjecture due to Gelander. So if x, so x will be as above, so let m be equal to gamma mod x. Let this be an arithmetic orbifold. Then there exist constants a, b, which depend only on x. Such that this m is homotopy equivalent to n, which is a simplicial complex with at most a times volume of m simplices, and such that the degree of each vertex is at most b. So this means roughly that when I know the volume, I can approximate my manifold by a simplicial complex whose topology and geometry is completely bounded in terms of the volume. And this is kind of a master theorem. All the other results about boundedness of Betti numbers or other topological invariants in terms of volume would follow from this. So now is almost over 20 minutes past. Now is the time where I will state the first result. So this conjecture, I mentioned it's now a theorem, at least in the case of manifolds. So theorem, this is due to myself, Raimbault, and Sebastian Hurtado. Yeah, I should switch their order because H is before R. Uh, 22, so it's an archive. So we basically proved that this conjecture, Gelander's conjecture, holds for manifolds. So it's very likely that our proof can be adapted for orbifolds, but this is kind of a different problem. So I'll talk a little bit about this, but I also want to mention a second theorem, which is about Benjamin-Schramm convergence. So same in the same paper. We proved that if the sequence gamma n, x mod gamma n is a sequence of congruence So I'll put two conditions: congruence or pairwise non-commensurable, or orbifolds. Then we have automatically that they converge Benjamin-Schramm to X. So in a sense, this condition that the sequence of arithmetic orbifolds converges Benjamin-Schramm to X is always satisfied unless you take a constant sequence. Right, so all those theorems about convergence of Betti numbers, they will hold for sequences of arithmetic orbifolds, and in rank 1, this is not. This is like there is a difference between non-arithmetic and arithmetic case. Well, in higher ranks, everything is arithmetic, so you might as well drop the arithmetic assumption.
Mikolaj, can I ask
Yes.
a question? A very
sure.
quick question on the conjecture of Gelander.
Up, yeah.
The constants A and B, it says that they depend only on X.
On X, yeah.
So they depend on gamma as well, or they just depend on G? They depend on
Depend only on G, so they shouldn't
Only
depend
on
on
G.
gamma.
Okay.
Yeah,
and
yeah.
in the theorems, do they depend on? They don't depend on gamma. They only depend on G.
Yeah, they only depend on G. In a sense, if they were allowed to depend on gamma, this wouldn't be an interesting theorem, because for every lattice, you will find some simplicial complex which is homotopy equivalent, because spaces are triangular. You can triangulate them. So yeah, the uniformity in X is the key point here.
Yeah, thanks.
Yeah. So this is congruence. Yeah. And this congruence condition, so one of those conditions is also necessary because in rank 1 spaces, you can have sequences of non-congruous arithmetic manifolds which do not converge Benjamin-Schramm. So some condition is definitely needed here. So since this is a number theory and dynamics seminar, I will talk about the proof of this theorem because it's more dynamical one. They both have common parts. So let me start with this common point for both those results, which is the arithmetic version of Margulis lemma. Yeah, so before maybe I go to this, I could mention that there are many results about Benjamin-Schramm convergence, but because I have limited time, I won't be able to mention them. But for example, in higher rank spaces, there are purely dynamical proofs that show that sequences of locally symmetric spaces always converge to X. So if you only cared about Benjamin-Schramm convergence, in some sense, our result is interesting only in rank 1. But our proof is independent of those other dynamical proofs. Okay, so arithmetic Margulis lemma. So let me start with the usual Margulis lemma. Which is sometimes called Collar lemma. So this says that there exists a constant epsilon equal dependent only on X, such that for every discrete subgroup, so this doesn't have to be lattice, lambda in G, the group generated by, or the group generated by following set. So this will be the set of elements lambda in big lambda, such that they do not move certain element of X by more than epsilon. So let me draw a picture here. So I have my space X here, some point small x, and I only take elements of lambda that move this point by a small amount. So this would be ball of radius epsilon around x. So yeah, so this group is virtually unipotent. And this is very often used in hyperbolic geometry and in general the geometry of locally symmetric spaces. This lemma itself, it cannot really be used to attack questions of on Benjamin-Shram convergence. But it turns out that there is a vast, you can find a very strong improvement of this lemma when you work with arithmetic lattices instead of discrete subgroups. And this is, we were quite surprised that this wasn't observed before, because it follows from it almost directly follows from a result of Emmanuel Briard. So let me state the arithmetic Margulis lemma. It says that there exists an epsilon positive dependent only on G. So I will recycle the notation for the Margulis constant, which is this epsilon, with the following property. So for every arithmetic lattice, gamma such that K is the trace field of gamma. So K, I'll define K as the Q generated by extension of Q generated by traces of adjoint representation of gamma, overall gammas in gamma. So for arithmetic lattices, this is a number field. The groups generated by the formula, given by the formula, very similar to the formula before. So let me copy this formula. So let me call them gamma x equals to gamma in gamma, such that the point x is not moved by more than epsilon. They should be virtually unipotent, but what changes here is that I'm allowed to multiply this epsilon times the degree of the trace field. So before, this was a constant. Now it's a number which grows linearly with the degree of the trace field. So those groups are virtually nilpotent, and furthermore, if gamma is compact, then they are virtually abelian. So this is great because we have this potentially very large radius. And we know that if we're the thin epsilon times degree of k thin part, there's essentially a cyclic group that controls this thin part. So yeah, it roughly tells us that the worst thing that can happen when you look at small translations is that the small point x will be translated by just a one family of group generated by essentially one element. So that's how the orbits will look like within the radius.
Ask a dumb question.
Yeah, sure.
What is meant by virtually here? I'm just not.
Virtually means that there is a finite index subgroup which is unipotent.
Okay, thank you.
Yeah, and in the proof we can actually in the paper we actually make this index explicit. So this index is at worst polynomial in k. So in degree of k. So we have control over this degree. So it's really not a huge deal to think that this group is actually cyclic. Oh, sorry, I said virtually abelian, but I should have said virtually cyclic. Yeah, this is even stronger. Yeah. Okay, so is that statement okay? So all we do afterwards is based on this lemma. Okay, so let me continue. So now I'll try to explain how do we apply this Margulis lemma, improve Margulis lemma to the question about Benjamin-Schramm convergence. So this theorem. So in order to apply it, I'll have to talk a little bit about invariant random subgroups. So and I'll specialize to the setting of symmetry of semi-simple Lie groups, but those definitions make sense for any locally compact group. So yeah, so sub G will be the space of subgroups. So this is space of subgroups H, subgroup of G, such that H is a closed subgroup. And topology, we select topology of Gromov-Hausdorff, of Hausdorff convergence. On bounded sets. So two groups convert, a sequence of groups converges to some other subgroup if in every ball their intersections converge with respect to Hausdorff convergence.
Oh, sorry, can I ask a dumb question?
Sure, I'm sure it's not a dumb question.
Okay, I'm not very sure the relation between this topology and the topology induced by the Hausdorff distance. So by Hausdorff convergence, are you talking about some metric like a Hausdorff distance?
Yeah. So I can draw a picture what this means. So I take a large ball in G. So let's say this is identity. I have some subgroup H that looks whose intersection of this ball looks like this, and a sequence of subgroups will converge. Let me draw in blue if they, for example, do something. Oh, this is too big. If they do something like this, so first group. So first group may look like this, then it looks like this, and they start to approach H in this ball. Okay, so that's how the convergence works. So in every finite ball, the intersections, let's call this sequence, let this be H and this was some Hn. So in this picture, Hn converges to H because the intersection with any ball converge in Hausdorff distance, and Hausdorff distance of the compact set is that they're close if they're both contained in small epsilon neighborhoods of each other.
Thanks. But is this topology same as the metric topology with respect to the Hausdorff distance?
Yeah.
Is it same as the Hausdorff distance topology, metric topology?
Yes, but you have the only difference is that you have to you would have to weight it with respect to radius, like according to radius of the ball. Because if you take the uniform Hausdorff distance for infinite sets, for any different subgroups, this will typically be infinite. So to get interesting topology, you need to restrict to balls and require the convergence in this metric on every ball.
Yeah, thanks. And you said this is defined on the bounded sets, but I suppose not everybody is bounded. So what is your space? Can I take a look at your space, the subgroups of P, right?
Yeah, space of subgroups. So this means that okay, let me write more.
Is everybody bounded?
I'll write like this. So Hn converges to H if and only if Hn intersected with a ball of radius r converges in Hausdorff distance to H intersected with ball of radius r for every r.
Okay. Oh,
so
thanks.
this defines topology for me.
Oh, the uniform in R as well.
No. This for fixed R, this has to converge.
For fixed R. Okay,
but there is no requirement for uniformity along all R's.
Yeah, thanks.
Okay. So why this is relevant? So it's not maybe immediate to see, but there is the dictionary between Benjamin-Schramm convergence of quotients and the weak convergence of the subgroups. So yeah, because I haven't defined what the IRS is. So IRS, invariant random subgroup, is a probability measure on sub G, which is invariant under conjugation. So this is a notion which generalizes finite index subgroups and normal subgroups at the same time. So let me give you a few examples. Mu can be Dirac delta at identity. Mu can be Dirac delta at normal subgroup. If gamma is the lattice, then I can define mu gamma as the integral. So 1 over volume of G mod gamma times the integral over G mod gamma of the Dirac deltas at the conjugates. So this is what we call an IRS attached to a lattice. So this is you're basically taking uniformly random conjugate of a lattice. Because it's a finite covolume, taking uniform random conjugate makes sense because the space of conjugates is finite measure. And now there is this useful dictionary that sequence of Benjamin-Schramm, sequence of quotients converges Benjamin-Schramm to X, this is equivalent to saying that sequence of those measures converges weakly star to the Dirac delta at identity. So you can translate questions about the about Benediction convergence into questions about convergence of measures on sub G. And this is where the dynamics enter the picture, because sub G is a G-dynamical system. Sometimes we have some classification theorems for how IRSs can look like. And this is very useful when you try to answer questions about the Benediction convergence. Now, since I have like 10 minutes left or something, let me sketch let me sketch how we prove it. So we'll need one more result about IRSs, which is called Zariski density for IRSs. So it's useful to think, sometimes it's useful to think of an IRS as a measure. Sometimes it's useful to think of a random variable with this distribution. So it's really a random subgroup. So there is a theorem proved by Bergeron and 5 other authors et al. In, I think, 2015. That if let's restrict to the case of simple groups to keep things simple, then all ergodic IRSs, all non-trivial, so non-trivial. Let me explain. Non-trivial in this context means that not equal to Dirac delta at the trivial subgroup are Zariski dense almost surely. Which means that if mu is such an IRS, then mu of the set of Zariski dense subgroup, Zariski dense subgroups, which is a measurable set of sub G, is 1 unless mu is equal to Dirac delta at identity. Okay, so if we have interesting IRS, it will be supported on this set of Zariski subgroups. This proof is very similar to the proof of Zariski density for lattices due to Furstenberg. So, well, unfortunately, I don't have time to comment on it. So now the strategy of the proof is following. Of the proof of Benediction convergence for arithmetic guys. Okay, so we'll take a sequence of arithmetic quotients. And let's assume, for simplicity, I'll show you a proof in special case. When degree of the trace field, so let's Kn be the trace field of gamma n. So in the special case where degree of the trace field goes to plus infinity, this is the most interesting case of the theorem, anyways. Okay, so we have there's lattices, arithmetic lattices, and we consider possible weak star limits of sequence of IRSs. So let me recall that mu gamma n was this average. So let me copy the definition of mu gamma n. Okay. So I will claim that the arithmetic Margulis lemma will imply that this limit is supported on the set of virtually cyclic subgroups. So claim arithmetic Margulis implies that any limit. So yeah, let me give some name to this limit. So let nu be a Wixter limit. So mu should be supported on virtually cyclic subgroups. Okay, how do we prove that? So yeah, we consider this. Consider a conjugate of gamma n. So let's write, this will be G inverse gamma n G, where G is some element of my group. So let me try to draw it in some large ball. So this is some ball of radius r in the group. This is identity. And suppose R can be large, but suppose we took n big enough so that this epsilon constant, Margulis constant, times the degree of the trace field is much bigger than R. So let's say it's bigger than 10R. Okay, so that the arithmetic Margulis lemma kicks in. So if we put small x to be equal to the class of G, the same G I see here, in big X, arithmetic Margulis lemma implies that this is a literal translation, so implies that the intersection of the conjugate of gamma by G with the ball of radius epsilon times the degree of the trace field. So this is the constant we have seen in the definition of this group gamma X. So this is precisely the conjugate of gamma X by G. This is virtually cyclic. So we know that when you look at the orbit of identity in this group, look at or just look at the intersection of the group with a ball, we'll see something that looks like a virtually cyclic group. So this is probably far from the real picture, but you can imagine it looks like this. Okay. And now with some work, we can show that this cyclic subgroup is actually of bounded index. And then when you look at this, any Hausdorff limit of cyclic subgroups of bounded index will be, whatever it is, it will be cyclic subgroup of bounded index. So of ball of radius 1r intersected with G inverse gamma G will be a virtually cyclic subgroup. Intersected with the same ball. Because the condition of being virtually cyclic of bounded index is actually a closed condition. So we'll never escape it. And this means that, okay, but this is it. This actually proves that all my limits that I can get, because R can be made to go to infinity. So we take R to infinity and deduce that the limit mu is supported on virtually cyclic subgroups. But then, so virtually cyclic subgroups in a simply group, they are never Zariski dense. So by Zariski density, for IRS, this means that nu is actually, it cannot have ergodic components which are non-trivial. So mu is the Dirac delta at identity. And then using this dictionary between bidimensional convergence and convergence of IRSs, we deduce finally that this means that the sequence of quotients converges bidimensional to X. And this finishes the proof. So I skipped some details. For example, I think in this proof, I assumed that G is simple. So, but this is the main idea. All other things are just some technical modifications that make it work in generality. So I think this is a natural place for me to stop. Thanks for your attention.
Thank you, Mikolaj. I think we can all upload the talk. Are there any questions for Mikolaj?
Can I ask a question?
Yes,
Sure.
of course.
Yeah. So, can I go back to the place where we define the random subgroup? Yeah, remember there was a formula. Yeah. Yeah.
This one?
Right.
Yeah.
So, so so in nature, okay, a random subgroup is a measure. Is that?
Yes.
A random subgroup is a measure. Is there a reason
okay, so it's like this. You can IRSs are formally random subgroup is a random variable with values in the set of subgroups, right? But all the properties we care about are already hidden in the distribution. So we only remember the distribution.
Okay, thanks.
So yeah, formally work with distributions. Sometimes it's just useful to say that random subgroup has this property. Well, surely then it's translated into a statement about measures.
And considering this formula, this mu sub gamma, so you are taking the average of the Dirac mass, and so mu sub gamma. Yeah, I'm trying to understand this mu sub gamma. This is so this is a measure on gamma. Sorry.
This is mu sub gamma is a measure on sub G. It's on sub G because the conjugates of gamma are no longer the subgroups of gamma, right? They're subgroups of G.
Okay.
So this point, this point gamma G is an element of sub G.
Okay. And do you generally have any existence for the random subgroup or the invariant measures under conjugation? Do you generally have the
Yeah.
existence?
So there are some cases when what I wrote here is exhaustive. So let me maybe write it here. So they're interesting. Yeah, this is interesting question. So for example, if G is higher rank with property T, then we have the following classification of IRSs. So ergodic IRSs are exactly are of the form Dirac delta at identity, Dirac delta at some h, where h is a semi-simple factor of G. So if, for example, G is a product of some groups, you can have one of those groups. You can also have the IRSs of the form mu gamma, where gamma is a lattice. In G or in a semi-simple factor. Sorry. Maybe let me to be simple, to have a simpler statement. I'll assume that G is simple. Okay. So then this guy, you can forget about this. So it's only Dirac delta identity, Dirac delta at G itself. Mu gamma, where gamma is a lattice in G. And that's it. So simple and adjoint. So there is a complete classification of ergodic IRSs. So we don't have much more. But for if G is equal, for example, to SL2R or SO(n)(1), and there is a like wild zoo of IRSs, which have uncountably many. They can be very weird. So it's basically as in the free group. I have very many constructions of IRSs. So there is a vast difference between rank 1 and higher rank.
So higher rank. Okay. What about you mentioned the property. What about G equal to SL(n)(R) for general N?
SL(n)(R). So for when SL(n)(R) and N is at least 3, then this previous classification theorem applies.
The property
modulo that it's not adjoint. Yeah,
okay.
Sorry, continue.
What is the property?
Property T is so property T is the property that when you have almost invariant vectors, in a unitary representation, it means we have invariant vectors. So this means, yeah, so for some groups, you can find unitary representations which have vectors that become more and more invariant under the group action. But there is no fixed vectors. But in property T group, this is impossible. In some sense, you cannot approach being invariant without having actual invariant vectors. This was discovered, sometimes called Kasdan's property, as property. T or Kasdan's groups.
Yeah, I'll look this up.
Yeah,
Yeah.
so this is very useful notion.
Yeah, thanks.
You didn't mention in the proof what the distinction between the co-compact case and the non-co-compact case, how you can get this improvement. Is there just a very quick reason as to how it's used?
Yeah, basically, in non-co-compact case, you can have actual unipotent elements and unipotent subgroups. That if you take X very close to the cusp of a symmetric manifold, a local symmetric manifold, then this group of elements that translated by less than epsilon eventually will become the whole. It can be the whole unipotent radical, and then it's obviously non-cyclic unless you're in SL2. While in compact case you don't have unipotence, everything is semi-simple, and once you know that this group gamma X is semi-simple, you can get the additional conclusion that it's cyclic, and this is some different approximation arguments.
But does that mean that the theorem should hold in a greater generality as well? No, like it should hold for thin groups when you make the distinction on space field instead.
Yeah, but this is a formal consequence because thin group is a subgroup of an arithmetic group. So
yeah, exactly. So that's not the volume part. The finite volume is actually not used. No.
No, arithmetic. So I think the only important thing really is the trace field. If you have a group which has a trace field and you control its degree, but you also, I mean, okay, I want to be careful about this. So for our argument to work, you need to know that the elements of your group that has the small translation, their traces actually generate this field, something close to this field K. Like generated bounded index subfield or something like this. So I'm not sure this will work in like complete generality where you just assume that you have a subgroup with some elements that are thin subgroup of a lattice, because we don't, even if you have thin subgroup of a lattice, you don't know if the traces generate like high enough degree or I mean, probably it could happen that elements of gamma X, they generate some small degree extension while the whole group generates a high degree extension. This will be a problem, but this cannot happen in arithmetic groups. In arithmetic lattices, yeah. But maybe it works.
Are there any other questions for Mikolaj? Then if not, I think we can thank Mikolaj again